Hello everybody, I want to do an example where I apply Snell's law to derive an expression for the critical angle. So let's draw a picture of the system. So imagine we have two medium. The bottom one is one medium, the top one is a different medium. And I'm going to draw a normal to the surface. And I'm going to label the bottom medium N1, or the incident medium. So N1 is the index refraction of the incident medium. So that's why I said N1 equals N sub I. And the upper medium is N2. The index of refraction is N2, and we can also call it N sub T. Because these are some of the ways they're labeled sometimes. Let's let light come in at some angle. We'll first call it theta 1. If the light comes in at an angle less than the critical angle, then light will go through and will be bent away from the normal. The angle of refraction will be bigger, or the angle of the transmitted wave will be larger than the angle of the incident wave. I want to look at the case where light gets refracted by 90 degrees. We call this the critical angle. And so all I got to do is apply Snell's law to calculate the critical angle. I will start with Snell's law, N1 sine of theta 1 equals N2 sine of theta 2. The value 2 here, the theta 2, is this 90-degree angle. So I'm going to substitute 90 degrees in here. And I'm also going to substitute theta critical. My goal is to solve for this angle. So this is 1. And so sine of theta c is N2 over N1. We take the inverse sine of both sides, and we get theta sub c. And I'm going to use arc sine instead of sine to the -1 because it's less confusing to students. And then I'm going to replace the 2 and the 1 with the transmitted and incident. And let's let the index of refraction of the incident medium be 1.345. Looks like water with some impurities in it. We can then calculate theta sub c as the arc sine of the N sub t, which is here it's going to be air, and it's probably salty water because normally this is written as 1.33. Now let's put our values in. N sub t is 1. N sub I is 1.345. And when you do this calculation, you get 48 degrees. If you look at that picture with the fish looking up, the light is going out at 48 degrees either way. So the fish can see through a cone of 96 degrees, which is twice this angle. So the light that's coming through and hitting, it's going to the fish, comes in at basically sweeps out a cone of 96 degrees, which is twice this angle. And it's very, this idea is similar to what you're encountering in the index refraction experiment that we're doing this week. So when light is incident on the surface, if you're below the critical angle, if you're going from more dense to less dense medium, if you're below the critical angle, what will happen is some of the light will get transmitted and some of the light will be reflected. The energy of the reflected ray, plus the energy of the refracted ray, the transmitted ray, has to be equal to the energy of the incident ray. When you're at the critical angle or beyond, all the energy stays in the same medium. There's no energy transmitted to the surroundings. This is one of the advantages of using fiber optics, because there's no energy lost to the surroundings. All right, thank you.